Welcome back to QBA 337. This is part of a two-course series. Starts with QBA 237, which is basic business statistics, and then we do applied business statistics in this course. So there's an assumption that you have done some sort of introductory statistics course previously. But it is possible that in the meantime, you've forgotten some or all of what you learned from that introductory course. So what I want to do is start off this class with a review of all the important things that you need to bring back to mind so that we can do hypothesis testing and I can teach you all about the applied statistics that we're going to learn about in this course. So we are going to begin where research begins, and that is with data. Our research is founded on data. So it's important that we know, what is data? What are data? Well, the data, those are the facts, the numbers that we collect as part of our research. We may collect information that is categorical. So for instance, I might ask you, are you a freshman, sophomore, junior, senior? That's categorical data. Which group do you fit into? Or I might ask you questions like, how old are you? How tall are you? And that's numeric information that describes something. It's a quality about you, but it's something that can be quantified, something that can be measured. Because we can use numbers or words, it's important that we understand when we see numbers just what job that number is doing. And there are four tasks, four jobs that numbers can accomplish. The first one would be, I can use a number as a name. If you've ever played sports, you got a number that was attached to your jersey, and that's how we knew who you were on the field. You had a number that stood in for you. But you have a lot of other numbers as well, like you have a social security number. You have an M number, that's for your student identification. And increasingly, you also have a phone number, which is becoming more and more your digital identity. That is you in the cyber world. And if you want to prove that to yourself, try changing your phone number and see what happens in all the websites that suddenly quit working and all of the tracking modules that are freaking out because it has a number attached to you. So that number is telling you one important distinction. It is telling you a difference. I can tell who you are as a student by looking at your student ID number. But what if we had some kind of weird dating game where we'll pay for a wonderful blind date and you get to pick from 3 people based only on their phone number? That would be difficult to do. You can't tell anything from the phone number. 3 different people, but you can't tell anything about the qualities of the person that would really matter to you on a date. So we can use numbers to indicate a difference, but there's another level of number that we can use, which indicates the order underlying the particular data set. So for instance, if I ask, are you a freshman, sophomore, junior, senior? The underlying order for your class standing could be indicated by numbers, or it could be indicated by words. And if it's numbers, we would number them in a sequential order. So we would say 1 is freshman and 4 is senior. So there is an indication as the numbers go up, class standing increases. It tells me a distinction, tells me a difference, but it also tells me something about the underlying order. There are other things that I could ask you about that are more numerically related, more quantifiable. So how tall are you? How old are you? The numbers that I'm asking you about come on a scale. They come on a measure where the differences between the numbers are the same all along that scale. And we're going to call that interval level data. So interval level data also tell us a difference. They tell us an order, but they give us something that can be quantified because of the equal intervals between the numbers. For example, one of my hobbies is doing woodworking, and I have a tape measure that my dad was using, and I kept it because it really illustrated this point well. When I was a kid, I'm sure I destroyed a lot of things. But now my dad is sort of paying me back, because whenever he uses my shop, he'll use my really expensive saw blade to cut PVC pipe and oriented strand board. And this time he left the tape measure on the board that he was cutting, and it cut off like the first 2.5 inches of the tape measure. Broke it. So now I have this tape measure that no longer has the beginning of the measure. Now, if I was in a pinch and I really needed to measure a board, a 16-inch distance, could I do that with my broken tape measure? I still could. I could maybe start it at 10 inches and measure to 26. I could do that because the intervals are the same anywhere along that scale. But the distinction between interval and ratio is whether or not the data have an absolute zero, a point beyond which we can't go below. Interval could be something like the temperature in this room. So if I ask, what is the temperature? And someone could look at the thermostat at the back of the room, and they could tell us a number. It's probably Fahrenheit. Could be Celsius. But in either one of those two examples, we can have 0 degrees on those scales, and we can also have negative numbers, degrees below 0. All right. What is that measure where there is a temperature that has an absolute 0, we can't go below absolute 0? The Kelvin scale. That is, you cannot go below that number. Now, the Kelvin scale is a little obscure, but there's a lot of other things that we use regularly, like money. Money has an absolute 0. You can't have negative dollars. You could have that little accounting trick that maybe the bank sends you a statement and says you have negative $13. That just means you owe them money. But there's no such thing as negative dollars. How old are you? Starts at 0, you can't be negative years old. How tall are you? Starts at 0, we can't be negative inches tall. We have a starting point, you cannot go below that. So many scales have the absolute 0 as a starting point. Now, the distinction between interval and ratio is something that we don't need to obsess about. It's important in some cases, but mostly we're just going to group these two scales together. We'll call them scale level measurements. Interval and ratio are scale level. They are quantitative variables. They quantify, they give us an amount. And then the categorical variables will be nominal and ordinal. If I ask everybody, how tall are you? I have a variable, anything that can vary or produce 2 or more different values. If I ask you about your height, like if I say, is your height a variable? What do you think? Well, not for you, no, because you're this tall, right? That doesn't change. So when we talk about variables, it's important to remember we're talking about group differences. This is something that can be measured across a larger grouping. If we have the height for everyone in class, can those numbers vary, take on different values? Absolutely. So it's that variance across the group that you're measuring. So you might have a constant height, but the variable across everyone will be called a variable. Data points can be categorical or qualitative. They indicate some quality of the individual or something that could be used as a grouping or a category. I can create numeric qualitative variables where I use 1 to stand for the control group and 2 to stand for the experimental group. I could use 1 and 2 to stand in for that nominal level data. Or I could use 1, 2, 3, 4 to stand in for ordinal level data like freshman, sophomore, junior, senior. I'm not limited just to numbers with categorical data. I could use letters or I could use words. I could use the words freshman, sophomore, junior, senior. That is an ordinal level variable expressed with words. I could use M and F to stand for male, female. Those are single letters. Words, I could use colors, I could use pictures. I could distinguish with non-numeric data between groups. On the other hand, there are some numbers that answer questions about how many or how much. Those are the scale level variables. Those are continuous or quantitative variables, and they will always be numeric. They can be interval or ratio, depending on whether or not they have an absolute zero, but in either case, we will always call interval and ratio scale level data to distinguish it from our categorical level data. Once we have variables, we're ready to do research. Research is this procedure for collecting, organizing, analyzing, and interpreting numerical data in a way to better understand the world. Well, let's say that we're going to do a survey. I draw up a series of 10 questions. I put them on a piece of paper. I hand everyone a piece of paper with these 10 items, and you answer those questions. I am collecting data. But when it's in that paper form, it's not particularly useful. So what I want to do is collect that data and organize the data into a spreadsheet so that I can more easily see the variables and the cases, and I can actually use that information. Analyzing is where I report back to you the average height of everyone in the classroom. The average GPA was this. We have groupings of people who are involved in sports and those who are not. Create that categorical variable. I can report back to you the analysis. But what's really fascinating is where I start looking for group differences. And do I find a difference between the athletes and the non-athletes on some other measure? That would be interpretation. What conclusions can I draw as the result of collecting and organizing and analyzing this information? That's the process of research. This would be an example of a data set. What I have done is taken information from a survey and put it into an organized structure, maybe using Microsoft Excel. And what we see here is some information about dogs. This is called the Dog Toys data set. This is one that I created back when we were all on lockdown from COVID. And I was at home, just me and the dogs. And I had to come up with some data set that I wanted to use, and it just seemed like, I'll make up a data set about the dogs. And that's where this comes from. It allows me to use the same data set over and over in each of the classes, so you'll see similar ideas. You get really familiar with this one data set. So let's start with this. I have variables in these columns. I have a certain number of dogs. If I ask you, what is the average number of toys owned? How would you respond? Well, it's really difficult to know how to respond to that because these data are raw. And raw data are not prepared to be served up. I can't tell you, you can't easily discern, are there more small, medium, or large dogs? You're just looking at raw data in a data set. It would be like going to the grocery store and getting raw meat and vegetables. It's food, it's edible, but you want to prepare it. You want to serve it up. You want to make it more easily consumable. When we have raw data, how can we make that more easily consumable, more easily understood? And the answer is we're going to use descriptive statistics. Descriptive statistics describe. So they will allow us to summarize and prepare data for presentation to the public. I might create frequency tables using numbers, so you can see the number and percentage of cases for each of the small, medium, or large sized dogs. I could report a mean or a standard deviation for the number of toys owned. Report the average number of toys owned and the variability around that average. I could create charts. I could create graphs. I could display the data so that you can see the pattern of the frequencies as they occur. And when I display the data, when I create charts and graphs, you're going to start to notice patterns. And those patterns are part of distributions. Displays of data reveal the distributions. Now, the distributions can be seen in examples like tables. So here I have a frequency table of attitudes towards statistics, scale of 1 to 10. I also have ordinal information for what is your favorite dog toy. I take that back. I have nominal information for what is your favorite dog toy. Or I can get really cute and I can use a stem and leaf plot that displays both the frequency and the raw counts of each of those data points. Now, all of these are showing you something about the distribution of the data within my data set. And when I look at these more closely, I can tell things that could be important for understanding what is occurring more or less frequently. But the type of distribution that we're going to use the most, that is the absolute most common data set in all of statistics, is the normal distribution. Any distribution where you have all of the scores underneath the curve, we'll call that place where all the scores are, that's the body of the curve. Most scores are there in that region. And as the frequency of those scores decreases, we get further out into the tails. So the tails are where the least frequently occurring scores are. Sometimes there will be a case that is so extreme, it's very different from every other data point in the distribution. We'll call that an outlier. If I have a normal distribution for height, I might have one person who is just especially tall, and that person, their height would be an outlier. And that could affect our interpretation of the findings depending on what type of outlier it is. So we need to know whether outliers exist, and we need to know what to do with them. Regardless of the distribution, there are 4 qualities that we want to be able to distinguish about that distribution so we can describe it and we can understand how we can use it. The first of these, if I am asking questions about, let's say, height, I might ask you, what is the height of the average American male? Well, the answer is 5 feet 10 inches. What does that mean? It means that if we have a normal distribution, most are going to be around that 5 foot 10 inch average. There'll be some that are taller, some that are shorter, but most of them will be around that average height. There'll be very few people that are 6'5", 7 feet tall and taller. There'll be very few people that are dramatically shorter than that. They're all going to be around that. That's the body of the curve. And what I am answering here when I tell you an average is where is the center of the distribution? Where do most of the scores tend to lie? But there's a second thing that I want to know because it tells me how useful that mean is. I want to know the variability. How spread out are the scores? The variability tells us whether the scores are very close together or very far apart. If we were looking at the average height for all the players on the basketball team, we would probably find that they have an average that is taller than normal, but they're going to be consistently tall. They're going to have low variability around that mean. All of them will be tall and they'll all be consistent in that. If I look at the whole student body, I'll find people of all varying heights. There'll be more variability. If all the scores are very similar, there's low variability. The measure of central tendency tells me a lot. If there's a lot of variability and the scores are very different, then the measure of central tendency tells me less. My measure of variability is a measure of how much I can trust my measure of central tendency. So I want to be sure to report on both of those. There's 2 other things that I want to know about my distribution, and both of them have to do with the tails of the distribution. Let's say I come to you with a really odd statistic, and I say, I've run the numbers, and I found that the average income for everybody in this class is $120,000 a year. And you think to yourself, that's odd because that doesn't sound like my income. Well, it turns out We have one student who's one of those geniuses that got into, I don't know, cryptocurrency back in the early days and is a multimillionaire, and that one person is skewing our data set. They're pulling the numbers out in one direction. So the third distribution quality that I want to explore is whether the distribution is symmetric, or is it skewed? Is it pulled out in one direction or the other? If it is pulled out toward the positive end of the scale, we call that a positive skew. Toward the negative end, we call it a negative skew. Remember, the skew is in the tail. That's where the outlier or the extreme scores are that are pulling in that direction. So you look at your normal distribution, and if it's pulled out toward the positive, that's a positively skewed distribution. The other thing that I want to know is about the tails being thick or thin. Now, this is something that is often discussed in terms of the peakedness or the flatness of the curve, but it's really not that. The kurtosis of a distribution has to do with the thickness or the thinness of the tail. The normal distribution that we've been looking at has qualities to it that allow us to say any scores beyond a certain pair of cutoff scores would be 5% of our distribution. So that's our normal distribution. It has these beautiful cutoff scores. There's another distribution that looks a lot like this normal distribution, but it's called the t-distribution, and it has thicker tails. There's more scores in the tails of this distribution than there is with a normal distribution. And this creates a problem, because if what you're measuring follows a t-distribution and you're assuming it follows a normal distribution, you have your cutoff scores at 5%, and yet, because of those thicker tails, you maybe have 7 or 8% of the scores beyond those cutoffs. So we have to fix that, and that was done for us by William Seeley Gossett, who was a brewer and a scientist with Guinness Brewing Company. Created these tables we still use for calculating how far we need to adjust a critical value according to a sample size if we're doing any kind of hypothesis testing or t-tests. We want to know the skewness and the kurtosis of our distribution so that we can make good decisions about the data. When we're doing sampling, we focus on the sample because that's what we have available to us, but it turns out that we're not really all that interested in the sample. We're much more interested in what that sample can tell us about the population from which that sample was drawn. We need to look at samples and populations. So let's say that you're cooking stew. The stew represents the population. Everything in that kettle, that is the population. That is everything that you want to know about. And what you want to know is, are the potatoes properly cooked? Is it seasoned the way that I want it to be? Does the barley need more time to? You want to know about that overall population. And so how are you going to determine whether or not the potatoes have cooked long enough? You're going to have some of that stew. You're going to sample that. But do you need to eat a whole bowl of the stew to find out whether it needs more salt or whether it needs to cook longer? No. You can tell everything that you need to know just from one spoonful of that stew, as long as one thing is true. As long as that spoonful is representative of the population. So what does that mean? It means that every element that is in the population is represented in the spoonful. So if the stew includes barley and potatoes and mushrooms, each one of those elements is contained in that spoonful. If I draw a conclusion based on a non-representative sample, in other words, I didn't have any potatoes in this spoonful, I could still tell you something about the population, but I could be wrong because my non-representative sample is excluding certain parts of the population, and I'm saying something is true that may not be true of some other excluded part of that population. So I want to be sure if I'm going to draw any conclusions that I have a representative sample, that all of the elements in the population are represented. Well, how do I get a representative sample? The best way to get a representative sample is to use a random sample. That means before I get my spoonful to try to determine whether the potatoes are properly cooked, I'm going to stir up the kettle. I'm going to get it all randomized, homogenized, so it's all the same, and then I'll just get a random spoonful, and as long as the elements in that spoonful have been represented, then I can tell whether the potatoes need more time or whether the stew needs more salt. I'm able to make those determinations with a small sample as long as my sample is representative. Now, the random sample doesn't guarantee that I have a representative sample, but it is the best way to get to a random sample. I want to learn about a population. That is the entire group about which I want to know something. And I want to choose a sampling method that will allow every element to be represented. So I want to be pulling from all parts of that population. So I have a really good sample. And then what I'm going to do is bring all of those data points together, all that, into a sample that should be a miniature version of the population. If I've used good sampling methods, then what is true of that population should be true of any sample drawn from that population. The parameters of the population should be represented in the statistics of the sample. This also means that if I draw a sample from a population, that what is true of my sample should be true of the population from which it was drawn. So if I don't know very much about the population, I could tell a lot from that good quality random sample. And the fact is that most of the time, we don't really know what we want to know about a population. So I said earlier that the average height of the American male is 5 feet 10 inches tall. How about the average American female? I don't know. It's like hidden. It's wrapped up. I can't peek inside. I don't know what the answer is. So if I don't know something about the population, how am I going to get that answer? Well, I'm going to start with a good random sample. That random sample is going to give me a mean. So I can take that mean. If that's all that I know, well then that's going to be my best guess of the population value. And other people are doing research and they're drawing other samples. And maybe some samples have a little lower mean and some samples have a little higher mean. And some samples are larger and smaller. Which one of those samples am I going to use to represent the population? The answer is I'm not going to use any one of them. I want to use all of them. I want to get like an average of the averages to use as my point estimate of the population. Now that we know about samples and populations, let me show you what we do with those samples to learn about a population. Let's do a research project that involves polar bears. Polar bears love to walk. They will walk 20 miles, 30 kilometers in a single day. Now, when I first learned this statistic, I was actually a little sad because I remember as a kid going to the Topeka Zoo, the Gage Park Zoo in Topeka, Kansas, and long ago, they had polar bears in these cages. It was toward the back of the zoo. And the thing that I always remembered about the polar bears was they were constantly pacing back and forth in their cages. As a little kid, I thought that was interesting because I could just watch them move around. And occasionally they would get in their cold water pool and they get out and walk some more. Well, it turns out polar bears want to be walking. They don't want to be in a 24-foot wide cage pacing back and forth. So the last time that I went to the zoo, I was surprised or was happy to learn that they've completely redesigned the bear enclosures, and now the polar bears have places to walk. Knowing that, we get interested in polar bears and how far they walk, and we discover that polar bears, on the average, will walk 100 miles per week. That is a population parameter. That is something that is known about the population. What we are going to do is draw a sample from that population and measure how far does that sample of polar bears walk in 1 week. Because what is true of the population should be true of any sample drawn from that population. If we draw a sample from a population that has a mean of 100, what do you predict will be the number of miles walked per week from that sample? Should be 100. What is true of the population should be true of the sample drawn from that population. And if I draw a second sample and measure how far they walk in a week, what do you expect that their sample mean is going to be? Should still be 100. If we draw a third sample from that population with a mean of 100, how far do you predict that they are going to walk in a week? Always going to be the same answer, 100. What is true of the population should be true of any sample drawn from that population. Now, this is the basis of the null hypothesis that we use in hypothesis testing. Where does that come from? The null hypothesis says there's no difference between the sample and the population. It comes from this. If you draw a sample from a population, what is true of that sample should be true of the population from which it was drawn. There should be no difference between the sample mean and the population mean. And if there is a difference, we're going to have to explain why there's a difference. Is it due to randomness or is it due to an effect? Our null hypothesis says no difference between the means. So I have these three groups that I have drawn from my population, and then I'm going to do something really stupid. I'm going to create not one, but two control groups. Now, the reason that's dumb is because you only need one control group. I'm doing this for learning purposes, but don't ever create two control groups for your research project. It's completely unnecessary. The control group doesn't get the treatment. They are the surrogate for, the stand-in for the population value. All right. Now I want to do an experiment with my polar bears. And in order to determine what I want to do, I'm going to do a literature review. I'm going to read what other researchers have done in their field and see if I can find a gap in the literature. See if I can find something that has not been studied yet. And so one evening, I'm reading my journals and I find this research report on whales. And the report tells us that whales that were given caffeine swim 48% farther than similar whales with no caffeine. And I do a quick study, a quick review, and I find out this has never been studied with polar bears. This is a gap in the literature. This idea needs to be studied with my population as well. I want to know, do polar bears who drink caffeine walk 48% farther than polar bears that do not drink caffeine? And that becomes my research project. My experimental group gets coffee, and my control group or groups get decaf coffee. And so they're being treated the same way, but one has caffeine and one does not. And after I have run this experiment, I collect data about my control groups and my experimental group, and here's what I find. The first control group, drawn from a population with a mean of 100, has a sample mean of 100 miles per week. And my question is, which of these groups is representative of the population? And this one is really easy. Because the sample mean is exactly the same as the population mean, it is a good representation of the population. It's a perfect representation of the population. They are exactly the same. There is no difference between them. But what about my second control group? They walk on average 104 miles per week. Is this number representative of the population? Well, it's not exactly the same. So I have to explain, why is it different? Is it different because, is there an effect? Or is it more likely that that 4 points, 4 extra miles per week was due to randomness, random chance, that I just happen to have a group that walked a little further than average? That second control group with a mean of 104, I'm going to assume actually has a mean of 100 with 4 points of measurement error. But when I look at the experimental group, I find that their number of miles per week is 150. Well, now I have another task. I have to explain this difference. When I consider my sample with a mean of 150, I know it was drawn from a population with a mean of 100. Does that mean of 150 represent the population with a mean of 100 plus 50 points of measurement error? Or is it more likely that it represents that experimentally defined population, that one where caffeine improved performance means they should walk 48% farther? I would expect that if the caffeine worked, they would walk 148 miles per week. In fact, they walked 150. Does that 150 better represent the population of 100 or of 148? And the way that I'm going to answer that is with probability. I'm going to calculate how likely is it that I would get a mean of 150 by random chance. If there really was no difference based on the caffeine, what's the likelihood I would get a mean of 150? And if less than 5 times out of 100 would I get a mean of 150 by random chance, I'm going to conclude that no, I think that caffeine really did work. It really had an effect. The caffeine has an effect of caffeine improved performance. The polar bears walk farther, just like the whales would swim farther. And with that, I conclude, yes, there was an effect. But there's one other thing I need to know. How big was that effect? So I'm not simply going to report that there was an effect, a statistically significant effect. I also want to report the size of that effect in something which is called effect size. Now, the effect size is the standardized mean difference. So what is a mean difference? In our example with the sample and the population, in that first control group, they both had a mean of 100. There was 0 mean difference. In the second example, 104 versus 100, there was 4 miles on average mean difference. And in the experimental group, there was a 50-mile mean difference. So a mean difference is the difference between 2 means. What standardization does is it works in the variability and also the sample size so that we get something comparable. We get an effect size that we can compare between studies. And this is not something we can simply do with p-values. It's important to remember that we cannot compare p-values. Let me illustrate this. We're doing a drug study. 2 drugs being tested side by side. We test the first drug and we find a statistically significant difference. It does improve the outcome statistically significantly, p less than 0.05. When we look at the second drug, we find that there was a difference, but it was not statistically significant. It did not vary statistically from chance. It was not statistically significant, p greater than 0.05. So with that, when you compare these 2 drugs, one which was significant and the other which was not, was that first drug more effective than the second? Now the intuitive answer is, well, if one was statistically significant and the other was not, well then the first one must have been more effective. But we cannot tell that just from p-values. We cannot compare significance versus non-significant and tell whether one is more effective than the other. Let me illustrate that with a different kind of example. There is this long-standing training seminar for leadership that has been demonstrated to statistically significantly improve team performance and productivity. It's been around for years. It was created by Professor Smith 30 years ago. Now, this program has been in use for a long time, and it is the gold standard. It's used because it's been demonstrated to work. If you want to improve productivity, you send your managers to this training program. You're going to see improvement in productivity. Beyond chance, it will be statistically significant improvement. Now, Jones is another young fella just trying to get his start in IO psychology. He has created a different leadership training that he wants to bring on as a competitor to the current training. And he wants to make it competitive by demonstrating that this old program that has worked so well in the past just doesn't work anymore. It used to be statistically significant, but now it's not. So he looks at Smith's original study. When Smith first created this long-standing gold standard program, he published an article in which he demonstrated that in his research that his program was statistically significant in its improvement. The T with 78 degrees of freedom was statistically significant, P less than 0.05. It made a statistically significant difference in performance. Now, Jones replicates that original study using Smith's program, and he reports the T of 1.06, probability greater than 0.3, non-significant. In other words, this program used to work, but it doesn't work anymore. It used to be statistically significant, and now it's not. But he's missing a very important piece, and that is effect size, which we can calculate from a t-value. So we can use 2t over the square root of n to standardize this effect size. And here's what we find. For Smith's original study, the effect size was 0.49. And for Jones's replication, the effect size was 0.47. They're essentially the same. There really is no difference in the effect size. One was significant, one was not significant, but they're measuring exactly the same thing. Why is that? The difference is sample size. A larger sample size makes it easier to find differences. And what we have was Smith's study having more power because those 78 degrees of freedom, that means there were 80 people in this study. There were two groups of 40, whereas Jones had two groups of 10, a total of 20 in his study. His study was underpowered. It was less likely to find statistically significant differences. It's a matter of sample size to determine the effect, not just the probability or the p-value. In other words, when it comes to significance testing, the difference between statistically significant and non-significant is not itself statistically significant. You can't compare p-values. So we're going to report effect sizes for all of the tests that we learn. Why do we do that? Well, one reason might be because APA style calls for the reporting of effect size. The APA says that we should report effect sizes even for small or non-significant findings, and that's useful. But maybe you are someone that doesn't like to be told what to do. Why should I listen to the APA? Okay, let me give you the statistical reasons why we always report effect size. So number one, we're not always doing hypothesis testing where we want to extrapolate back to an overall population. Maybe what we're doing is just a pilot study. We have several different drugs that we want to try out. What we do is just test them sequentially. We do multiple tests, and we're looking for the drugs that are most promising. Which ones have the greater effect? Well, if you want to know which drug is most effective, report the effect size. If you're not really doing hypothesis testing, moving from sample to population, effect size is really all you need to know. Now, the second example is something that I ran into a lot when I was working with professors and students, especially with a lot of student research, the sample sizes tended to be small. So maybe you have a sample size of 12. It's because you're testing a relatively rare phenomenon. What happens is you do your study and it turns out to be non-significant. And that means it's not publishable. Well, we can rescue that. So what happens is there's other researchers in the country who are doing very similar research to what you're doing. If everyone reports an effect size for their research, we can do a meta-analysis. Even though all of the studies are non-significant, the effect sizes are still robust. They can still be used. And we can get an overall picture of how well this phenomenon actually performs. We can see what is actually happening, not disguised by the lies of random chance or the p-value being too small. Now we can go the other direction. We can have a sample size that is so large that every difference is significant. I was doing a study with junior high school students. We had 2,000 or more students, and it was such an overpowered study that any difference that I found was statistically significant. But because it was overpowered, it was finding differences that really didn't matter in the real world. Think of sample size as magnification. If you're looking for an effect, the more magnification you have, the easier it is to see that effect. But if you're using, let's say, an electron microscope, you can find effects that are microscopic. Like if you've ever felt a piece of highly polished stainless steel, it just looks so smooth. But if you looked at it with a microscope, you'd see deep gouges and scratch marks. They are really there. But honestly, in the real world, in the world that we inhabit, when you rub that stainless steel, it's perfectly smooth. There's something there, but it doesn't matter in the real world. That can happen with research. We can find statistically significant differences from an overpowered study that don't really matter in the real world. That's what happened with our study. The effect sizes were less than 0.1. They were just tiny, and they were real, but they didn't translate into a really effective program that was helping to reduce the outcome that they wanted to reduce. It was statistically significant. It just didn't have the effect. So here's the thing. Regardless of what type of research you're doing, there is really no reason why you would fail to report an effect size for your study. And this is why, as we continue to work, I'm going to show you how to calculate an effect size for each of the new tests that we learn about. So what I want to do is wrap up really where we began. Let's talk a little bit more about data. We collect data, we organize the data so that we can analyze the data. A data set is our organized set of data. All of the data that has been collected for a particular study. We're going to place this information into a spreadsheet. I'm going to begin working across rows. So for each new piece of paper that I pick up, for each new survey, I'm going to start for this case and I'm going to write all of the information across a row. And as I have collected information on multiple people, all those rows are going to add up so that later on I can look down the columns, and this column is for how tall, here's the weight column, here's the GPA column. Every column is a variable. And collectively, this is called a data set. This is that dog toys data set that we looked at earlier. All of this together is my data set. But there's parts of that we need to know exactly what they are. For instance, in this first column, column A, those numbers, those are just identifiers. That's not actually a variable. But we do have variables like toys owned and favorite toy and dog size. The number of dogs represented in this particular small snapshot of a data set, each one of those we could call elements. The participants or the subjects, those are the elements of the data set. The cases, those are what run in rows. The variables are in columns. Toys owned is a variable. Favorite is a variable. Across the columns, we could call these observations. So each individual data point for each case is an observation, and every cell could be described as a data point. So here's the difference. Data points, observations, they're really functionally the same thing. Your number of observations will always be the same as your number of data points. And of course, each variable has a certain level of measurement to it. The favorite toy variable, where we have answers like chirpy bird and stuffed monkey and chew toy, is nominal level. If I represented it with numbers like 1, 2, 3, 4, 5, those numbers are just representing a category. It's a difference, but there's no underlying order. It's nominal level. Small, medium, and large, however, that has an underlying order. So dog size is going to be an ordinal level variable. And when I ask how many toys do you own, I'm getting a number that has an equal distance between each interval, like 1, 2, 3, 2 toys is twice as many as 1. That will be a scale level variable, and because you can't have less than 0 toys, a negative number of dog toys, it's going to be ratio level. But both interval and ratio level we're going to call scale level data. These data points were collected as a one-shot survey. It was a snapshot. So we will call these cross-sectional data. If I were to repeat this study multiple times over several different time periods and follow-ups, or let's say I were to take the scores for the tests in this class where we have test 1, test 2, 3, 4, that would be time series data, information being collected over time, or something's called repeated measures data. So we have cross-sectional data. In this example, we'll also learn how to use repeated measures or time series data. And that is your review of what you should remember from your introductory statistics class and what you'll need to know to do well in this applied statistics class. Thank you so much for being here. I'll see you guys next week.